Okay. All right. So part two. Okay. So transport processes. Um, so when we talk about flow, fluids are gases and liquids. Okay. Um, in physiology, we deal more with liquids, but gases are fluids too. Okay. So they flow, and that flow is controlled by pressure gradients. Okay. Um, so they always go from high concentration, or they always want to go from high concentration to low concentration, high pressure to low pressure. Okay, cell membranes are selectively permeable. I'm sure you've heard that many times. Okay, so now we talk about transport plus membranes. Okay, so passive transport, active transport. Passive transport does not require energy. Okay, active transport always does. Okay. Okay. Diffusion is a very passive process. It always goes down the concentration gradient, down the chemical gradient from high concentration to low concentration. Okay. It is the net movement is until the concentration is equal, which is equilibrium. It is very rapid over short distances. Okay. Um, but as you increase distance, you dramatically decrease the rate it works. Okay, that's why you need simple squamous cells to allow for diffusion over short distances. Okay, it is directly related to temperature. So the higher the temperature, the faster the diffusion rate occurs. Okay, it's inversely correlated to molecular weight and size. So the bigger the molecule is, the slower it will diffuse. Okay. So here you go. So you tell the brown dot diffuse a lot faster than the red dot because it's smaller, or because it's smaller in terms of Daltons, 166 versus 697. Okay. All right. So you can read the table by yourself, but make sure it makes sense to you guys. Okay. All right. Ions do not move by diffusion. That is somewhat. So let me fix that. Ions do not move only by diffusion. Okay. The ions movement is influenced by chemical gradients. Okay. If you have positive charge on one side, it's attracted to negative charge on the other side. Okay. So like charges repel each other. So the more positive charge I have on one side, the more they want to get away from each other and go to the other side. Okay. The ion movement is a combination of chemical gradients, okay, and electro gradient, where charge where the chemicals are and where the electrical signals are. Okay. So, for example, if I have sodium by the side and I have potassium by the side, the sodium wants to come across this membrane because there's so many sodium on this side and there's no sodium on this side. But because this side there's a lot of positive charges, okay, not so much. If you have negative charges here, the positive charges are more attracted to the negative charges than they want to come across the membrane. So there's a combination of effects that is not purely diffusion. Is what they're trying to say here. And that gradient is called the electrochemical gradient. Okay. Okay. So additional properties, okay. Lipophilic molecules move by simple diffusion, okay? If you're lipophilic means loves fat. You can move across phospholipid bilayer relatively easily because the phospholipid bilayer is mostly fat, okay? All right, so here you go. Okay, make sure you understand this picture here. Okay. All right, protein mediated transport. Okay, this thing is proteins. Okay. So membrane proteins have four major functions. One of them is just structural proteins. So they hold the membrane together, they hold it to anchor it to other cells. Okay. Those are the boring ones. The more important ones have function. Membrane proteins for membrane transport, structural proteins that hold kind of the shell together, and then membrane enzymes and membrane receptors. Okay. Okay. So the ligand binds to a cell membrane receptor protein right here. Okay. The cell membrane receptor can either do one of two things. It can either trigger a direct reaction, like there'll be enzymes underneath here that causes a slight change. That slight change will cause these enzymes to go off, and it will cause some events to happen in the cell. The more likely thing is that receptor will get folded into the like it will undergo endocytosis and get folded into the cytoplasmic vesicle here, and then the ligand is released and it triggers something happening inside the cell. Okay, we will go through both examples in a little bit. Not in this chapter, but in other chapters. Okay, the channel proteins form open water-filled passages. Okay, so these are designed as a water-filled pore. So one thing, water can get in. This is one of the ways water actually gets into or out of the cell. Okay, through these channel proteins. The other thing is the channel is designed for ions to come through. Okay, so chloride ions, sodium ions, potassium ions, these can all go through their own individual holes. Okay, you have two types. Okay, open channels are usually open. Okay, pores are usually open. They're always open. There's no real way to close them. Gated channels work by a gate. Okay, we usually draw them this way, where you have an open gate versus a closed gate, and it looks like a human gate or human door. In reality, the gate looks more like a ball and chain, and that ball just shoves into the hole and blocks something from happening. Okay, this is a more realistic drawing. This is just a more easier to understand drawing. Okay, these are channels, so you can see that there's a hole, like these four proteins leave a hole in the middle in between them where water or ions can come through. Okay. Okay. So carrier proteins change conformation to move molecules. I'll get into that in a second. But first, some definitions. Uniport carriers allow for only one thing to come across. Okay, so a sodium channel will be a unique port that only allows sodium to come across. Okay, you can have co-transporters which allow two things to come across. Okay, if they come across together, then they're symport. Okay, symport means two things bind on one side of the membrane, both things move to the other side of the membrane. Antiport is the opposite. Antiport, okay, is this. Sodium gets pumped out, potassium gets pumped in, okay, at the same time. So symport, antiport, okay, uniport, okay. All right. So carrier proteins, this is how they work, okay. They allow, basically, there's two gates. There's gates on the extracellular side and intracellular side. One gate is open, the thing comes in, that gate closes, the other gate opens, and the molecule moves through, and then that gate closes again, and that gate opens again. And so you keep, it forces the ships in this case to move in one direction. And again, it's the same thing, it forces the ions to move in one direction. Okay, so you can see that here. Okay, this is Glute Transporter. Glucose transport is really important and something that you definitely have to understand. Okay, so Glute transporters, you can see it goes from high concentration to low concentration. So it comes in, right? These type of Glute transporters, okay, goes against with the concentration gradient, so high to low. Okay, so no energy is involved. Okay, active transport move substances against their concentration gradient. Okay, so they always use ATP somehow. They do not have to use ATP directly. Okay, like before in other classes, we teach you like they use ATP directly. That happens a lot of the times, but not always. Okay, so primary directed active transport uses ATP directly. Secondary indirect active transport uses ATP to establish a gradient, electrochemical gradient. Moving that gradient now allows you to move other things in. Okay. So if you generate a bunch of ions on one side of the membrane, that is membrane potential. That potential can be used to do work. Okay. Okay. Let's take a look here. Okay. Okay. So the last thing we'll explain in this short little video is the sodium potassium pump. Okay, the sodium potassium ATPase, it uses ATP to make this pump. Okay. Okay. So right here, so this is an ATPase. I am pumping out sodium, I'm pumping in potassium. Okay, so this is the mechanism. Okay, I take three, I'm gonna start from up top. I take three sodiums from inside the cell. I flip it and I release them, and I pick up two potassiums and I bring them back into the cell. Okay, and since I'm going against the concentration gradient, I have to burn the ATP right here to do it. Okay, so let's look at this a little bit more trickily. So I'm moving three positive charges outside, and I'm only taking in 2. So every cycle, I'm depositing 1 positive charge on the outside. Okay, so the outside of the cell will become more and more positive charge. In other words, the inside of the cell will be more and more negative charged. Okay, so we always view the thing from inside the cell. So the inside of the cell is negatively charged, and the outside of the cell is quote unquote 0. Okay. Okay, and all of this because of the sodium potassium pump. Okay. Okay. So hopefully, make sure you guys go through this and make sure it makes sense to you guys. Okay. All right. So, okay. So remember, right here, I have pumped all the sodium on the outside of the cell. So now I have a bunch of sodium we're dying to get in. It uses ATP. I've spent some ATP. I've spent a bunch of ATP now to get all the sodium on the outside. Okay, and I've established a electrochemical gradient for sodium to want to come rushing back in. Okay, because not only is there no sodium inside the cell, and therefore sodium wants to go from high concentration to low concentration, the inside of the cell is negatively charged. So sodium, being a positively charged molecule, wants to come in. Okay, so we are going to take advantage of that. And when we bring in sodium, we're going to use it to bring in a glucose as well. So sodium glucose transporter, co-transporter. These two coming at the same time. Okay. Okay. I hope that makes sense to you guys. I'm going to end this video right here. And there will be a part 3 for chapter 5.